Dr. D. Sangeeta is currently a senior lecturer at the Department of Chemistry, Anna University, Chennai. She has completed her PhD in the field of polymer chemistry from the University of Madras in the year 2000 and has teaching and research experience of more than 10 years. Her research interests are in the following fields: fuel cells for clean energy, functional membranes for desalination, and polymers for biomedical applications. She has published more than 20 research articles in national and international journals and has more than 40 research articles in national and international proceedings. Presently, she is guiding 6 research scholars for their doctoral degree.
Welcome to the UGC lecture series. Today, in part 8 of Synthesis of Polymers Unit 2, we are going to discuss about what polycondensation or step growth polymerization is, and then finally we will be looking upon the techniques, the methodology that is used for the polymerization of the different monomers. There are importantly 4 or 5 methods that are basically or commonly used for the preparation of different polymers. These techniques are called as bulk polymerization technique, solution, emulsion, gas phase, and suspension polymerization. Then overview about the whole second unit will be dealt today. Coming to the step growth polymerization or polycondensation, shortly called as its kinetics. Let us now consider a reaction that is happening between 2 substances which are basically the monomers. Let the first one be the ethylene glycol, whose chemical formula is HO, CH2CH2OH, and the second monomer, let me put it as terephthalic acid, which has got an acid COOH and COOH terminal functional groups along with the unit C6H4. Now let me call this as the XAX plus YBY, where A and B are the long in between methylene chains of the 2 monomers, and X and X are the functional groups or the alcohol functional groups at the terminal ends, and Y and Y are the acidic functional groups in the second monomer. When they are condensed together, they form. We have to note the word that it is getting condensed. That means a condensation, a reaction, a chemical reaction is taking place between the 2 monomers to form a new monomeric unit. Basically, the 2 functional groups available in the 2 monomers condense together to form a new monomeric unit with the expel of one small unit, which could be water or hydrochloric acid, whatever it is. In this case, it is going to be the water simple molecule that is going to be going out. And the new monomeric unit that is going to be the basis or the formation of the polymer is going to look like this. X and Y will be at the terminal and these chains will be joined together. Now, both the monomers taken in equal molar concentration in this case, and let me call the initial concentration of each of these monomers as C0. I am assuming the concentration of the monomer initially are the same, and let it be represented by C0. Now, we already know that the number of functional groups in each reactant or the each monomer molecule is going to be 2, that is bifunctional because of the 2 functional groups at the terminal ends. Therefore, the functional group concentration is given by N0 is equal to 2C0, where C0 is a concentration of the monomers available and N0 is a functional group concentration. This is given by 2 times the C0 concentration. Let me say that the reaction is going for a time t. After time t, the concentration, let it become C. From C0, the concentration now after time t is becoming C, and let me say P be called as the extent of the reaction. Then a relation which combines these 3 terms is given by C is equal to C0 into 1 minus P, where C0 is the initial concentration and C is a concentration at any given point of time t, and P is called the extent of the reaction. And similar to this, we can also say N is given by N0 into 1 minus P, where N is the number of moles of the functional groups at any particular time t. Hence, the average degree of polymerization at time t is given by dP is equal to concentration of the initial number of functional groups divided by the concentration of the number of functional groups that are available after the time t. This is once again expressed as N0 by N, which is again equal to C naught concentration by C concentration. This can also be written as C naught concentration by C naught concentration into 1 minus P, where P is the extent of the conversion. This is once again shortened as the relation is given by dP is equal to 1 by 1 minus P. And this is a very famous equation, and this equation is called as the Carothers equation. Carothers equation is a one for the polycondensation processes, and thus the degree of polymerization is proportional to the extent of conversion P, and hence dP increases with the increase in the P value. Since this comes in the denominator with a negative sign, we can say that degree of polymerization increases with the increase in the extent of conversion, that is your P value. Now the other part of this episode is all about the techniques, which is the last part of this unit. We are going to deal with the different techniques or the polymerization methods that are going to be utilized for the preparation of the different polymers. Basically, why there are so many types of techniques that are available is you have the different types of monomers which has different characters. They could be basically a solid material, or it could be a liquid, or it could be a gaseous substance. Accordingly, you have to suit your methodology to prepare the polymers out of these different states of materials. Or certain polymers can easily form a beautiful polymer only in the presence of the catalyst and an initiator, or certain other monomers, they require a medium to support them. The medium could be a solution bath or a solvent bath, or it could be an emulsifying agent or a stabilizer. These things may be necessary for polymerizing certain types of monomers. So depending upon the characteristics of the monomers and the polymers that are going to be formed, sometimes certain polymers will be powdery in nature, it would be cross-linked polymer sometimes, or it could be in the form of a particular bead shape, or some other shape should be wanting for you. So the processing method is decided depending on the different types of the properties that is available with respect to the monomer and that is required in your polymer. Hence you have 4 or 5 types of polymerization techniques that are very commonly used in the laboratory. They are called the bulk technique, solution, emulsion, gas phase and suspension. Let us see one after the other now. The first very simple type of polymerization is called the bulk or the mass polymerization. This is carried out within the monomer itself. That means I don't have to depend on any other solvent or any other medium for the polymerization to be conducted. I have a pure monomer, I have the initiator, I have the catalyst, I initiate the reaction, the polymerization is done with the vessel over there. Such reactions are catalyzed by additives like initiators and chain transfer agents, or light or heat are also necessary for sometimes for making your initiator to be present there. If it is a free radical, the free radical should be formed by decomposing the basic molecule. So these things are the very basic necessities for a polymerization to take place, and such reactions are very effectively happening only in the presence of the monomer and such important constituents that are required for effectively making the polymerization to happen. There are no other supports that are used in such type of polymerization. But when we try to talk about the advantages and the disadvantages of such methods, the bulk or the mass polymerization method has got some limitations. For example, they are highly exothermic in nature. This is because the heat that is liberated due to the polymerization reaction does not get dissipated very easily because I don't have a supporting medium. So that becomes a difficult part. So it could be highly exothermic, and other demerit is that non-uniform molecular mass distribution can be formed in the formed polymer. We know what a molecular weight distribution curve and a molecular weight distribution is all about. The different polymeric chains of the polymer that is formed, each and every chain they have a diverse molecular weight, or average molecular weight is highly diverse. Then you call it as a non-uniform polymerization, whose molecular weight differ from one molecular chain to the other molecular chain in a wide range. So that would be possible only in such bulk polymerization. This is because you don't effectively control the movement of the molecules that is taking place by itself. Wherever the monomers are available in the reactor vessel, the polymerization goes on and there is no movement effectively happening, and there is no big control over the polymerization that is continuing in each and every chain. So you have highly dispersed polymeric species that are formed. That is why it is called a non-uniform MWD system. And of course, you may require perfect agitation. It requires a agitation and separation process. Agitation is required basically because of the reason that the monomer may not come in touch with the initiator, because it's a simple system where you don't have a medium once again. So you may have to give a stirring or an agitation continuously to have a uniform dispersion of your initiator and the catalyst in the system, so that the reaction is taking place everywhere. And of course, this will also contribute to the formation of a little bit more uniform molecular weight based polymers also. And you need to have a separation or isolated step where the polymer is separated from the reaction vessel. Suppose a polymer that is going to be formed, in the case of polystyrene, styrene is a liquid monomer. When it is going to undergo the bulk polymerization technique, the polystyrene becomes a solid. So you have to have a appropriate method and way to remove the polymer from the reactor vessel. So the separation becomes another important step in the process. But there are definitely some useful merits due to these reactions. For example, usually you have a pure polymer that is formed. This is also basically because of the reason that you don't have any kinds of contaminants that are added into the system, because you don't have any solvent, any other extra stabilizing agents are never added in these systems, and hence you expect the polymer to be highly pure in their form. This is because of the recipe that contains primarily only the monomers. Those monomers or polymers that are formed by these bulk polymerization technique includes vinyl chloride, vinyl acetates or polyvinyl chloride, polyvinyl acetates, polyacrylic esters, and so on. They are very effectively formed by this particular technique. Coming to the second type, or the solution polymerization method. Here in this case, as the name tells you, there will have to be a solvent or a solution medium where the polymerization is taking place. So in addition to the monomer, initiator and catalyst, you require a medium to carry the reaction in the system. So both monomer and polymer in this particular type of polymerization are soluble in a suitable solvent. And another important requirement is that not only the monomer should dissolve in that solvent, but the formed polymer should also be dissolving in the same solvent. Then only you will have a uniform bath for the protection of the polymer in the system. Of course, there are some advantages and disadvantages with respect to this type of polymerization also. The advantages are that easy heat dissipation. This is naturally when there is an exothermic reaction taking place, large amount of heat is going to be developed, evolved, and they get easily dispersed or dissipated through the solution path or the solution medium. And a relatively uniform molecular weight is also obtained. This is also because of the same reason that you have a uniform mixture and it is spread throughout the solution bath, and you finally end up with a relatively uniform molecular weight based polymer product. But coming to the disadvantages of this method, naturally you may end up with an impure product. This may be due to the foreign bodies or particles or your solution contaminants that could be present along with the solvent. And of course, low molecular weight is also another limitation of this method. This is because of the reason that the chain transfer to the solvent can also take place, whereas in the bulk polymerization, because of the absence of any other solvents or any other extra molecules, the chain transfer may happen only to the monomers, or the termination becomes difficult there, and until all the monomers are consumed, the reaction will be continued, and that is why it's a highly exothermic process too. But whereas in the case of solution polymerization, you may have a termination step very easily happening because of the chain transfer happening to the solvent molecule itself. But in the first case, in bulk polymerization, if you want, you can deliberately add or purposefully add a chain transfer agent or a particular molecule which is required to terminate the reaction. That can also be done in the first system. This is about the solution. And the third type of polymerization, let us have a short break and then continue with the other types of polymerization. Welcome back after the short break. Now let us go into the third type of polymerization, which is nothing but the emulsion polymerization. As the name tells you, there is an emulsifying agent that is added into the system. You basically have a liquid monomer which is dispersed in an insoluble liquid to form an emulsion. And most of the time, very commonly used dispersion medium is your water, and the liquid monomer is going to be well dispersed without getting dissolved in the water medium. Now the monomer is in the water emulsion, which is going to contain also the catalyst and are going to be stabilized by the presence of the emulsifying agents, which are basically the surface active agents, or shortly called as surfactants. The role of the surfactant is to have a stabilized condition. They play the role of emulsifying property and make the monomer to be available in a dispersed form throughout the medium or throughout the emulsion, your water emulsion. And the recipe is going to contain all these following. In addition to the monomer, you have the water, which is basically immiscible with the monomer. This is important. Or any other medium which is going to be an immiscible medium for the monomer, and a specific emulsifying agent called the emulsifier or the surfactant, and the concentration of such surfactant should be above the critical mesial concentration, which is shortly called as CMC. This is very important. This emulsifier or the surface active agents concentration should be sufficient enough for getting dispersed throughout the medium, and these emulsifiers are formed in various forms throughout the system, and the polymerization is effectively happening within the within every mesial that are going to be formed throughout the reactor. And this concentration, when it is going to be above the critical value, a particular value, then only the polymerization will be facilitated. And of course, the water soluble initiator. Although the monomer is not soluble in the water medium, you have the initiator which is basically soluble in the water medium, which is very much needed for initiating the reaction that is going to take place because of the different mesials that are available in the bath. So this could be schematically represented in this particular picture. These are the different emulsifying agents. They are the ions of the molecules in aqueous solution, your water solution. If you look into each of these emulsifying agents, there are two groups. One is hydrophobic, this tail region, and this head region is hydrophilic in nature. So when the critical mesial concentration is reached above a particular concentration, they form what is called the mesials, and these different mesials are well solubilized with the monomer within the system. So if you look into this particular closed structure, all these emulsifying agents, they arrange themselves in a particular order, and inside you have all your monomers present. And these phobic regions are towards the monomer, and the philic are towards the water medium because they are attracting towards the water. And when these monomers are added to the initiator, which is basically soluble in the water medium, which initiates the reaction and the polymerization forms, then you can see that this mesial is getting swelled. This is an example for the swollen polymer molecule, where the polymer is growing, a polymer chain is growing to form a polymer, and this mesial is also swollen in its nature. And this mesial is responsible for holding each and every polymer chain growing throughout the system. So this is how the emulsion polymerization is happening. The most important thing is the monomer is available within the system without getting dissolved in the water medium, and you have the initiator which is basically soluble in the medium, and you have to have the concentration of the emulsifying agent in the correct form or above the critical mesial concentration, so that it allows or facilitate the polymerization to effectively happen throughout the system. Now these monomers, though they are insoluble, has some limiting solubility in water, where light solubility will be available. The large dispersed droplets are stabilized by the surfactant adsorptions, the solubilized ones in the hydrophobic core of the mesial. So the solubilization takes place because of two regions, that is your hydrophobic core and the hydrophilic shell portion, which is attracted towards the water, and each one of them they form a mesial. The molecularly dissolved state in water. All these three conditions are required for an effective emulsion polymerization to take place. The most commonly used initiators for such systems are BPO, your benzyl peroxide initiator, or a redox system can also be utilized. And this type of polymerization takes place within the surfactant mesyl concentrations, which is around a size of about 10 nanometer, very small, which basically grows in size at the dispersed monomer droplets where the size is going to be larger, that is around 1000 nanometer. Once the polymerization is complete, the polymerization will have to be isolated from the emulsifying bath either by evaporation or by coagulation. After the separation, subsequent filtration and drying is also required to remove your final product. The disadvantage of this method is they are not pure, because you have to add the emulsifying agent, your medium, everything comes into the picture, and the degree of polymerization is usually high in such cases. The other type of polymerization is the gas polymerization. As the name tells you, you have a gaseous monomer system to form a polymer. For example, ethylene is a gas, propylene is a gas, but when they form a polymer, they become a polypropylene solid or polyethylene solid. So it is a different type of polymerization technique used for gaseous monomers. This takes place with the formation of a liquid phase, or the polymer melt, or a solid polymer is going to be formed. This can be schematically represented by this particular diagram, where a tubular flow reactor is shown. Ethylene becomes polyethylene, and this is your monomer. CH2 double bond CH2 goes into the reactor vessel. It slowly goes into the reactor vessel through this pipeline, wherein a suitable catalyst is provided, a suitable atmospheric pressure is maintained at a particular temperature. It's a high temperature, high pressure bath, and the reaction takes place. Of course, a continuous stirring or agitation is also provided, and finally this is allowed to come out, and those unreacted gaseous monomers are removed at the top, and the polymers, which are basically liquid or a solid, are removed at the bottom. The last type of polymerization is the suspension polymerization. This is also called as the pure polymerization because of the reason that the formed products are bead forms or pearl shaped products are formed in this type of technique. Here in this case, monomer containing initiators, modifiers, etc. is dispersed in a solvent. Generally used solvent is water, by a vigorous stirring. Along with this vigorous stirring, you also add up the stabilizers, which are basically protective colloids like cellulose and polyvinyl alcohols, or the surfactant or the surface active agents are also used as a stabilizer. The polymerization is allowed to take place within the dispersed monomer particles, and agglomeration is mostly prevented by making use of the stabilizing agents. Once the reaction is complete, the polymer is again separated by either centrifugation or filtration, and finally it is washed and dried. The difference between the emulsion and this type of polymerization is that in that you have to maintain a critical mesyl concentration with the help of the emulsifying agent over there, whereas in this case the monomer containing the initiator, modifier, everything is dispersed within the aqueous medium, and a stabilizer is particularly added to prevent the agglomeration of the monomer particles throughout the system. And each and every suspension polymerization is equal to a number of bulk polymerization. If the bulk polymerization is going to take place in a micro scale within the whole system, a number of multi-number of bulk polymerization taking place at every place in a big bath, then you equate this to a suspension polymerization technique. So in summary, what we have done today is we have covered with the polycondensation method, its kinetics, and then we went on to the techniques of polymerization. The 5 important techniques we have dealt with: the bulk polymerization, solution, suspension, emulsion, and gas phase polymerization. We have talked about the methodology, how these polymerizations are conducted, their advantages and disadvantages. With this, the whole unit is coming to an end. And in this unit 2, in all the 8 episodes, what we have done is given as an overview here. We begin with the polymerization types, the basic chain polymerization. We have talked about the kinetics and the mechanisms with respect to free radical polymerization technique and the ionic In ionic, we have done with cationic as well as anionic kinetics. And then we moved on to the coordination polymerization method, which is also called as a stereoregular polymerization method because of the reason that you obtain highly uniform isotactic stereoregular polymers, which are highly designed in a uniform packed method to get a highly uniform product by making use of this coordination polymerization. With a great extent, we also dealt with the Ziegler-Natta catalyst type of polymerization in this topic. Then we moved on to the copolymerization methods, how they are different from homopolymerization, and finally we touched upon the step growth polymerization or the condensation polymerization, wherein we talked about the copolymer equations, its derivation, and the Carothers equation. The kinetics and mechanisms were dealt with in an elaborate manner. And finally, we did the different polymerization techniques in a detailed fashion. Here are few questions. What are the various types of techniques used for polymerization process? Compare the bulk and solution polymerization. List down the merits and demerits of emulsion polymerization method. What is critical mesial concentration or CMC shortly, and what is its significance? What are surface active agents and what is its role? Mention the precautions that is to be undertaken for gaseous polymerization. What is a pure polymerization and what is Carothers equation? Thank you.